Welcome to Excel and Business Math video number 43. Hey, in this video, we got to talk about the power of compound interest and how to calculate future value of a lump sum. Now, here are the amazing topics we're going to cover in this video. And here's a picture of the awesome FV, future value function. This function and the math formula we will learn will help us figure out the future value of some lump sum amount of money that we put in the bank. So for example, if we put 10,000 bucks in the bank at 4% compounded once a year for 10 years, future value will tell us how much we have in 10 years. Now, last video, we talked about not compound interest, but simple interest. And so our first topic is we want to compare and contrast simple interest and compound interest. Now, we're going to start off by going to our PDF notes. The PDF notes in the Excel files you can download below the video. Now, we want to compare simple interest and compound interest. Simple interest, as we did last video, means interest is paid or earned on the original principal only. That means if we borrow $100 and we pay 10%, we only pay interest of $10 each year. But compound interest is different. Compound interest is interest paid or earned on both the original principal and interest reinvested from prior periods. Now, we want to look at this example, a loan of $100 for 4 years at an annual rate of 10%. And then we'll compare simple and compound interest. Now, the trick for simple interest is that every year, 1, 2, 3, 4, we're taking the actual original principal. That's the amount we borrowed. Every time it's the same amount, and we multiply it by our annual interest rate to get 10 bucks. So look at that. There's 4 tens. The interest paid is the same amount each year. So if we did the calculations, well, we could actually just take the 10, multiply it by 4, and add it to the 100, and the maturity value is 140. Now, for simple interest, the concept is the amount we multiply by the annual rate is the same every year. But now let's look at compound interest. Well, in year 0, that's when we take out the loan, the balance is 100 bucks. So guess what? When we go to calculate the interest for year 1, we take the prior balance of 100 bucks. Hey, 100 times annual rate of 10%, that's 10 bucks. So look at that. We add the 10 in, and that means the balance after 1 year means we owe $110. But look at this. When we get to year 2, we actually take the amount that was in the account at the end of 1 year, and we use it as the amount to multiply by the annual rate. So here we take 110 times 10%, 11 bucks. Then we add it. And at the end of 2 years, 121 bucks is sitting in the account. And then, of course, whoop, we use that for year 3 interest calculation to get 12 and 10 cents. We add it. At the end of year 3, we have 133 and 10 cents. We use that in year 4 to get the final interest amount. When we add it up, look at that, 146.41. So with simple interest, we pay 140 on maturity date. But with compound interest, we have to pay 146.41. Now, we'll do these calculations in Excel in just a moment, but I want you to notice something. 146.41 and 140, if we subtract those two, $6.41, that is called interest on interest. Now, this is from a loan perspective. For us, that means we would be paying $6.41 more in interest if we did compound interest. But if we were the bank, or as we'll see, if we deposit money into a savings account that uses compound interest, that means we will earn $6.41 more of interest because of compounding interest. Now let's go over to Excel. Now over here in Excel, I'm on the sheet S or C, simple interest or compound interest. Here's the same loan. We borrow $100 for 4 years with an annual interest rate of $10. There it is, our formula inputs, the principal, the annual interest rate, and the number of years. Simple interest, compound interest, we want to calculate the total owed at maturity date for both of these. Now the amount owed, I'm going to say equals that $100 because at time 0, that means the day we take out the loan, we owe $100. Now we get to year 1. Well, we need to calculate the interest. Equal sign, I'm going to click on the $100 times, and I'm going to click up here on D4. That's our formula input for annual interest rate. Now I'm going to lock this with the F4 key because I want to copy this down. But get this, since this is simple interest, we always need $100 as we copy the formula down. So I'm going to click back somewhere touching D11 and hit the F4 key. That's it. $100 times 10%, Control-Enter. It gives us $10. When I double-click and send it down, go to the last cell and hit F2, that worked all the way down. Now, to calculate the amount owed at the end of each year, we simply do a formula. This is sort of like our checkbook formula. Equals one cell above for whatever the balance was in the account from the year before as a relative cell reference, plus whatever interest we calculated this year. Both as relative cell references. Control-Enter, double-click, and send it down. Now I'm going to go to the last cell and hit F2. When I hit Enter, there it is, 140. Now down here to compare and contrast, maturity value for simple interest, equal sign, and I'm simply going to get that 140 and Enter. Now let's do compound interest. Well, the amount owed at time 0 is exactly the same, equals, and I'm going to click up on this 100. And then I hit Enter. Now, the year 1 interest earned equal, well, in this first year, we're actually going to have the same numbers for both simple interest and compound interest. I need the amount that was in the account from the previous period times this annual interest rate of 10%. Now I'm going to lock this, F4. Here's where our formula for compound interest is going to be different. Whereas with simple interest, we lock this because we wanted $100, the original principal, each year. Here we don't want to do that. I'm going to leave it as a relative cell reference, which is one cell up and one cell to the right. That way, when it gets down to subsequent cells, it'll always be looking at the previous balance. Now I'm going to hit the Tab key. Now I want to do the formula, which is the same for compound and simple interest. Hey, whatever was in the count from the previous period plus whatever interest we just calculated. Now I'm going to hit Enter, and I'm going to highlight both of these cells with different formulas, point to the fill handle, double-click, and send it down. Now I want to make sure and go down to both bottom cells, F2. That's looking good. It's taking the 133.10 times our 10% annual rate, Tab, F2. And that's correct also. Whatever the balance was from the previous year, plus the interest we just calculated, and Enter. And there it is, $6.41 more because of interest on interest. When we compare simple interest to compound interest in this first example, we clearly see that with compound interest, whether we're paying it on debt or receiving it on our investment, compound interest will give us more than simple interest. Now, I need the maturity value, also known as future value when we do compound interest, for the compound interest loan. So I'm going to equal sign, click on that, and Enter. Now I'm going to do a formula equals up arrow, compound interest maturity value minus up arrow, up arrow. There's the simple interest maturity value, $6.41. Now, this example was for a loan. We compared simple interest and compound interest. But we want to make sure and understand something. If we borrow this $100 and we pay back for compound interest 146.41, for us, we're paying $46.41 in total for interest. But remember, there's two sides to every financial transaction. If we borrow $100 and that's debt to us, to the bank, they lend out $100, and to the bank, that's an investment. So we want to go over to the sheet, two sides. There are two sides to every debt financial transaction. Now, actually, there's at least two sides to every financial transaction. We just happen to be talking about debt here. The debt side for compound interest loan, we borrowed the principal, $100. In 4 years, we pay back maturity value. There it is. And the interest paid is $46.41. But that's us. The bank looks at it from the other side. It's an investment. And this is the investment side for the compound interest loan. The bank lent out the principal, $100. In 4 years, they receive the maturity value. Interest earned, $46.41. Here, you borrowed the money. Now, I want to go over to the sheet Simple and Compound 2. And look at that. I already completed this for you. And the reason I did that is the only difference is perspective. Imagine that you deposit $100 in a savings account for 4 years at an annual interest rate of 10%. Well, you're depositing money, and the contract says they'll pay you either simple or compound interest, but the calculations are exactly the same. Simple interest calculations and compound interest calculations. So if you deposited 100, you love it because on the maturity date, you get 146.41. That means you deposited 100, and over that period, you made 46.41. Because the contract gave you compound interest, you made interest on interest of $6.41. Now, for this transaction, let's go look at the two sides. Oh, here's you right here. You're on the investment side for a compound interest savings account. You lent the principal? See, we don't think of it that way. When we put money in the bank, we think of it as our money. But what are you doing? You're actually lending the principal to the bank. The bank actually uses your money and goes out and loans or uses the money to try and earn a higher rate of return than they're paying you. But when you put the money in the bank, you're actually lending the principal to the bank. In 4 years, the account has a maturity value or a future value of $146.41. The interest earned, $46.41. Here's the bank. Even though you deposited the money, it's debt. Actually, the bank, when you put money into the bank, they have to record it as debt. They actually owe you the money. The debt side for the compound interest savings account, the bank borrows the principal of 100. In 4 years, they pay back the maturity value or future value, and there's the interest paid, $46.41. Now, as we start to talk about compound interest and not simple interest, we got to talk about new terms. So I'm going to go over to the sheet New Terms for Compound Interest. On this sheet, we want to look at the terms for compound interest. Now, we'll compare and contrast the terms and variables we used for simple interest and compound interest. Now, for simple interest, we didn't use this term, but for compounding, we'll use this term, lump sum amount. That just means the single amount either borrowed or invested. Now, that just means for a lump sum, we drop it in the savings account or we borrow it. And then time goes on, and at the end of all the time, we either have to pay it back or we can withdraw it. So lump sum is the amount we have at the beginning. Over on the simple interest side, we use P for principal. Principal was the amount borrowed, lent out, or invested. over here on the compounding interest side, we're not going to use principal, although principal is still used sometimes in compounding interest problems. When we're calculating either with math formulas or our Excel formulas, instead of principal, we're going to use present value. That'll be PV. And present value will be the lump sum amount borrowed, lent out, or invested at time zero. Now, at time zero, that just means the moment you borrow the money or the moment you put the money in the savings account. Present value. It is the present value of the amount at time zero. Now, maturity value, MV, maturity value, that was the total for principal and interest. Over on the compound interest side, we're not going to use maturity value. We're going to use future value because we'll have some present value. We'll put it in the bank account or we'll borrow it. And then in the future, there'll be some future value that we either get to withdraw if it's an investment or pay back if it's debt. So future value will be the value of the lump sum debt investment at the end of all the compounding periods. Now, maturity date is exactly the same for both simple and compound interest. It just means the day that the future value is paid or earned. Over here, we would say the date that the principal and the interest is due. It's just the final day that we either withdraw it if it's an investment or pay it back if it's debt. On the simple interest side, we used R for rate, and we called it annual simple interest rate. Over here on the compounding interest side, all we do is refer to it as annual interest rate. When you see annual interest rate, it implies compounding. Now, normally what you'll hear is they'll say 10% interest rate compounded monthly or daily or quarterly. So it will always be implied that it's compound interest. It's only on the simple interest side that they use the word simple to distinguish that this annual interest rate is a simple annual interest rate. Now, when we do our formulas, we're actually going to see some math formulas and some Excel formulas. When we're doing the math formulas, I'll write little I to represent the annual interest rate. So annual interest rate, usually given as, and you probably heard this before, APR. That means annual percentage rate. Now, on the simple interest side, we had T, which meant time. That was a fraction of a year. We also used term. That meant how long was the loan or the investment. Was it in days, months, or years? Now, we don't have direct parallel variables on the compound interest side. Instead of using time, fraction of a year, and term, we're going to use number of compounding periods per year. So if the annual interest rate is 10% compounded monthly, then N, that's our math variable, total number of compounding periods per year, that's 12. So if interest is paid once a year, N will be equal to 1. Interest paid quarterly, every 3 months, N will be equal to 4. Interest paid daily. Surprisingly enough, a lot of savings accounts at banks pay interest daily. So the N will be N equal to 365. That means they have to add the interest to your savings account every day. And the next day when they calculate your new interest, it includes all the previous daily interest that you earned. Note, the bigger the N, like 365, the more the interest will be. Now, years, we're going to have annual rates for a number of years given a certain number of compounding periods per year. We'll use in our math formula X to represent years. That'll be total years for the debt or investment. Now, we have to calculate period rate. Notice little I divided by N. That means we take the annual interest rate and we divide it by number of compounding periods. Period rate is very important because they almost never give you the period rate. They always give you the annual interest rate. So you're going to have to calculate what the period rate is. Now, here's an example. Bank account pays 8% compounded quarterly. That's what it'll say in the contract. Then, to calculate interest rate per quarter, or our period rate, We take 8% divided by 4. There you go. You earn 2% each quarter. Finally, we have to calculate total number of compounding periods, x times n. That means years times number of compounding periods per year. So if years are 4 and n is 12 compounding periods per year, 4 times 12, uh-oh, I don't have Excel. I think it's 48. So the total number of compounding periods would be 48. All right, if you get confused, you can come look at this sheet here for what the variables mean. It's also in our PDF notes. Now, before we can see some awesome formulas for calculating the future value of how much we put in a bank or how much we borrow, we have to go talk about cash flow. So I'm going to go over to the sheet cash flow. Now, for compound interest calculations in Excel and in an advanced finance class, the direction of cash flow matters. You always think of cash flow in regards to your wallet or purse, because sometimes it will be confusing. But if you immediately just say, what direction is the cash going? Is it coming into the wallet or purse, or is it going out? If you remember this little trick, is it coming in or is it going out? You'll always get the cash flow correct. Is the cash flowing into your wallet or purse? Well, if it is, that means we're going to have to record it in our Excel functions as a plus. So if we have borrowed a loan, that means we get $100 from the bank, so it's coming into our wallet or purse. We'd have to record it as plus 100. Into the wallet or purse, positive cash flow. Is the cash flowing out of your wallet or purse? Surprisingly enough, when you deposit $100 into the bank account, even though it's your money, remember, you're taking it out of your wallet and giving it to the bank. So out of the wallet has to be recorded as minus 100. Out of the wallet or purse is always a negative cash flow. Now let's scroll down here. Now to emphasize cash flow, let's look at an example where the bank lends you money and you borrow the money. At year 0, the bank lends the principal. That means it's minus 100 to the bank. Out of the bank's wallet or purse goes $100, and then you get it. On your side, from your point of view, at year 0, you borrow the principal. It has to be recorded as a plus, because guess what? You just went to the bank and asked for money, and they gave it to you. In 4 years, when there's a maturity value, here's the bank. Oh, yeah, they lent it. So as a positive number, the full 146.41 comes into the bank's wallet or purse. From your point of view, in 4 years, you have to pay back the maturity value. So, of course, it's a negative to you. It comes out of your wallet or purse, and it goes to the bank. All right, be sure to use the wallet purse trick to figure out if the cash is positive or negative. Now, before we go to the next sheet and see our first example of a future value calculation, I want to go over to the PDF notes. On page 5, there's all the terms. Page 6, there's our beautiful math formula. And on page 8, there's our awesome Excel function. Now, just to take a moment to look at our future value math formula, we're going to calculate the future value by taking, yes, the present value amount, multiplying it by, in parentheses, 1 plus the period rate. If that's 8% and that's 4, that would be 0.02. So inside the parentheses, we'd have 1 plus 0.02, and there's our caret. That means exponent. In parentheses, if we're doing it in Excel, we have to multiply years times number of compounding periods per year. That will give us the total number of periods. Now, in Excel, when we do this, we're going to make it easy on ourselves. We're going to calculate period rate in a separate cell, and we'll calculate total number of compounding periods in a separate cell. But if you ever had to do the formula straight through in a single cell, that's how you do it. Here's all of the variables, and there's a simple example. In fact, our Example we'll do over in Excel, there's how to do it on paper. Looking at our Excel function for future value, there's that awesome picture of future value. We're going to have to use the rate argument, the NPER argument, and the PV argument. Here's a little table. And the three values we're going to need inside of our future value function, here they are. PV, both in the math and the Excel, they're exactly the same variable. Period rate, that's how we do it with our math formula. That's what the Excel function is going to ask for, rate. Use this diagram and don't get tricked. Don't put annual rate or something into this argument. You put rate, look at it here and go, oh, yeah, that's the period rate. Then total number of periods, there's the math formula. And they named this argument in the Excel function per, which means number of periods. For us, we know it's total number of compounding periods. All right, let's go over to Excel. Now I'm over here on the sheet formulas. And example number 3, what is the future value of a savings plan if you deposit $100 in a savings account for 4 years with an annual interest rate of 10% compounded yearly? Well, here's our variables. Present value, that's the amount that we put in the savings account. So at time 0, $100 is what we put into the account. X, that's years. Looks like 4 years, so I'm going to put a 4 and enter. Annual interest rate, 10%. I'm simply going to type 0.1 and enter. Number of compounding periods per year. Well, this one's easy. It's yearly, 1 and enter. Now we need to calculate period interest rate. Now we could, if we wanted to, simply use the 0.01 because dividing by 1 won't change it. But we're going to use this formula over and over, and we want to accommodate the fact that this may change. So I'm going to, for the period rate, say equals, there's the annual rate, divided by the number of compounding periods per 1 year, which happens to be 1 in our case. So when I hit enter, I get the same annual rate as period rate. Total number of periods, same thing here. When we take 4 total years times number of compounding periods per year, well, this one's easy because there's only 1 compounding period. This is the one situation where your total number of periods is exactly equal to years. That means 1 compounding period per year. All they're going to do is calculate the interest at the end of each year and put it in the account. Now, future value the long way. Well, let's do this one last time the long way. Year 0, how much did we put in the account? Equals, well, that $100 and enter. Now we want to calculate the interest. So year 1, well, the formula is going to be equals always up 1 and to the right 1 because I always want to look at previous year balance. This is year 1, so I'm looking at year 0 balance. And I'm going to leave that as a relative cell reference. So as I copy down, when I get to year 4, it'll be looking at the correct year 3 total times, and we do not want annual rate. We want period rate. I need to lock that, so I hit the F4 key. All right, so that will work. Tab. Now we want to do our balance formula. Equals whatever was in the account from the previous period plus the interest that we just calculated for this period. Now when I enter, I can copy both formulas down, both different formulas, highlight, double click and send it down. Check the last cell, F2. It's got locked on the interest rate, and it's got the previous balance. That's perfect for our interest calculation. Tab, F2. That one's looking good too. Now the longhand future value equals, well, there it is. Enter. Now, that's the last time we're going to do that. Let's go ahead and calculate it using our math formula. It's listed over here, but we made it easy on ourselves. We calculated period, interest rate, and total number of periods. So you ready? Equals the present value, that's the amount at time 0, times, in parentheses, 1 plus the period rate, close parentheses, Shift 6 to get our exponent because we're going to raise it to the total number of periods. And that will work when I hit enter, exactly the same number. Now let's try our Excel function, FV equals FV. There's our function. Rate, that's the period rate. So I click on period rate, comma, NPER, number of periods. That's the total number of compounding periods for the entire length of the investment in our case. Then I'm going to type a comma. Now, the PMT argument, we're not using that argument when we're doing lump sums. Because for a lump sum, that means we simply put this in the account and let it sit there till maturity date. 2 videos ahead, we'll talk about savings plans where we put a certain amount in each period. And we'll use the PMT argument 2 videos ahead. But for us, for a lump sum, you don't put anything here. You actually totally skip it. So watch this. I type a comma. That means for the PMT argument, it's empty. Now, present value. This means the lump sum we put into the bank, and we have to think about cash flow. Well, it came out of our wallet and into the bank, so we have to put a minus first, and then we click on the amount. So present value is going to be minus whatever is in cell C4. Now, there is a 5th argument called type, and that goes along with a period payment when we use PMT. And we'll get to see how to use that argument 2 videos ahead. So it's the final argument. So we actually just close parentheses and leave that argument out. Now, I want you to notice something important here. When we skip an argument that has variables that we entered in on either side, you have to type a comma and skip it. But when we get to the last argument or the last few arguments and we're not going to use them, you don't even put them in and do not type a comma. Now I type close parentheses, and that's our formula. When I hit enter, exactly the same thing. So we saw here F2, how to use our math formula, enter F2, and for the first time, how to use the future value function, enter. Now we want to go ahead and look at some other examples for calculating future value. I'm using my arrow to move the sheets, and now I want to go to FV1. All right, example 4. If you deposit $5,000 in an account for 5 years that pays an annual rate of 5%, compounded quarterly, what is the future value? We have to list our variables. So present value, that's the amount at time 0, 5,000. And for that 5,000, we have to ask, what's the cash flow direction of the present value? Well, 5,000 deposited, that means it's coming out of our pocket. There it is, out of the purse or wallet and into the bank. So we're going to have to make sure and enter that into our Excel function as a negative. The annual rate, APR, or little I, that's 5%. I type a 5. We can see that it's pre-formatted because the percentage symbol pops up. Compounding periods per year. Quarterly, that means we put a 4. That's our little n. Years, it says 5 years, so 5. Now we can calculate our period rate. Annual rate divided by number of periods per year equals, there's our 5%, divided by quarterly 4. That will give us 1.25% per quarter. Total number of compounding periods, years times number of compound periods per year. There's our years, 5 times 4 times a year, they'll calculate interest for us and enter. So 20 total periods, and each one of those periods will use 1.25. Now we can calculate our future value. I'm going to use the equals FV function, the rate. Don't forget, that's the period rate. There it is, 1.25%, comma, total number of periods, that's 20, comma. We don't have any quarterly payments for this lump sum example here, so I'm going to type a comma to skip that. The present value, it's going into the bank but out of our wallet. So I'm going to put a minus and then click on 5,000. We don't need the last argument, so we simply close parentheses and enter. Now, we should round that because all the rules are met. We're dealing with money. We definitely have the potential of extraneous decimals, and we're going to use it in a subsequent calculation. F2, and right after the equal sign, I'm going to round that whole future value calculation, comma 2, close parentheses, and enter. Now we can say, hey, there's the future value, and when I subtract how much I put in at time 0, 5 years ago, enter. There's the interest we earned, $1,410.19. Now I'm going to check the future value equals present value times in our math formula, in parentheses, 1 plus the period rate, close parentheses, caret, that's our exponent, raised to the total number of periods. And when I hit enter, there it is. We have checked it, $6,410.19. Now, for this example, this was us putting money into the bank. So this was our investment. And we're happy we got 1,410.19 pennies earned in interest. Now, let's go over to FV2, and we're going to read this problem. If you borrow $5,000 from the bank for 5 years that charges an annual rate of 5% compounded quarterly, what's the future value? How much must we pay back in one lump sum in 5 years? Well, these are the same exact numbers we just did, but now we're doing it from the other point of view. We're borrowing, not investing. I put our present value of 5,000, annual rate of 5, number of compounding periods per year. Number of years, I've already calculated period rate and total number of periods. So the future value function calculation goes like this. Well, the rate, that's the period rate, it's exactly the same, comma, NPER, exactly the same, comma, we have no payment, so we simply skip it, present value. This is a positive number. It's coming into our wallet, so we leave it as a positive. We skip type because we're not doing period payments. Now when I hit enter, watch what future value does. It's smart enough to know that at the end of all those periods, that's the amount coming out of your wallet or purse. There it is. Whoop! 6,410.19 goes to the bank. Now, to calculate total interest paid, I'm going to take the full minus amount. That's the amount coming out of our pocket. And I'm going to add the amount that we got at time 0. When I hit enter, that's a subtraction because that's the amount of interest coming out of our pocket. That's the amount of interest we paid in total on this debt. We could check the future value equals, there's our present value times, in parentheses, 1 plus period rate, close parentheses, caret, and there's the total number of periods. When I hit enter, it checks out. There's the future value. Now, we want to go look at example number 3. I'm going to click on FV3. And I want to do a calculation based on simple interest over 10 years and then compound interest for the same investment for 10 years and then plot it and see what happens over time as we compare simple interest and compound interest. Now, here it is. We deposit $5,000 in a savings account for 10 years with an annual interest rate of 10% compounded yearly. I've entered all of our variables, and I calculated period rate and total number of compounding periods. Now, I want one formula that I can create and copy down. And the goal of this formula is to tell us how much is in our savings account at each period. Year 0, 1, 2, 3 for simple interest, and then do the same thing over here for compound interest. But I'm going to first kind of cheat and just start. Let's see if I can calculate the interest and copy it down. Well, wait a second. This is simple interest. So if I take right here in cell B14, 5,000, that's the original principal, or in this case, we'll call it present value, times, and there's the annual simple interest rate. Now, right now, if I were to hit enter, that gives me 500. But what I would like is as I copy the formula down, 500, then 1,000, then 1,500, and so on. Well, I can easily do that because I put the years off to the side. So watch this, F2. Now I'm going to have to think. That principal or original amount we put in or present value is 5,000. I need it all the way down, so I'm going to hit the F4 key to lock it. I also need to lock the interest rate, so F4. Now if I simply multiply this by the number of years, in our case that's number of compounding periods too, as a relative cell reference, Control-Enter, double-click and send it down. All it did was it took the 500 and it multiplied it appropriately for simple interest times the number of periods. So at the end, 10th year, the total amount of simple interest we earned, $5,000. Now I'm going to hit F2 because I really want the total balance, not just the interest. Well, I'm going to add the original principal or present value. I'm going to hit F4 to lock it, Control-Enter, double-click and send it down. This gives us a running balance of the amount in our savings account for each year. 5,500 at the end of the first year, 6,000 at the end of the second year, and so on. Year 10, we have $10,000 in our account. Now, this formula will work if I copy it up because the whole interest calculation is being multiplied by 0. Now, if we look over here at our chart, I want you to notice that it's an even pattern. The slope of this line, or the amount that it goes up, is the same every year. It's exactly $500. Now, when we do our calculation for compound interest and plot it, it'll look a lot different. Now, how are we going to do this? Well, we can use the future value function. And since that's the present value and that's the period rate, we can enter both of those numbers into our future value. But for total number of periods, as we copy down, I'll use the number of years as our NPER, and it will be a relative cell reference. So you ready? Equals FV tab. The period rate, that's that rate right there. It's got to be the same all the way down, so I hit F4, comma, NPER. This is where I'm going to get tricky and click as a relative cell reference on the year, comma. We have no payment, comma, the present value. It is a minus because I am depositing this at time 0, so minus the 5,000, and I need to lock that. So F4, no type, close parentheses, and that will work. Control-Enter, double-click and send it down. All the way at the end, F2. I'm just checking the cell references. Actually, I think I forgot to do that over here, F2. OK, that's all looking good. But look at that. It calculated the running balance in the savings account. Every single year, they add the interest, and it builds up. $12,968.71. That's a lot more than this $10,000. Now, I'm also going to copy this up because it'll work the same here. F2, that entered in at 0 just gives you the value at time 0. And enter. And if we look at our chart, the orange line represents the compound interest. And look at that. By year 10, it is much bigger than our simple interest. In fact, simple interest grows the same each year, but compound interest grows more and more quickly as the years move on. All right, now we want to go look at our next example on the sheet, FV4. All right, example 7. If you deposit $10,000 in an account for 15 years, that pays an annual rate of 6.5% compounded daily, what is the future value? Now, compounded daily, that means we have to figure out how many compounding periods per year. You would have to read your contract. We're going to assume this is a year with 365 days. Years, 15, and enter. So we need to figure out our period rate. Well, we have the annual rate. We're going to actually have to divide it by 365, and this will be a very small number. So divide it by 365 and enter. So I'm not going to even add the formatting. But there it is, our daily interest rate. Total number of periods equals, there's the number of years times number of compounding periods per year. When I hit enter, that's a big number. 5,475 compounding periods. That means each day the bank has to put interest into your account, and then the next day they calculate interest on interest. Now the future value equals FV tab, the rate. That's the period rate, and that is very small, but it's our daily interest rate, comma, NPER, that's the total number of days, comma, we don't have a payment, comma, the present value, this is us putting money into the bank. So when we put it in the bank, it comes out of our wallet. So we enter a minus, and then that cell reference. We don't have a type, close parentheses. And how much do we have in the account after 15 years? We have $26,509.37. That is the power of compound interest. I'm going to add the round just to be consistent with our rule, comma 2, close parentheses, and enter. Now I can calculate, hey, there's the future value minus, that's how much we put in, and you got to be kidding me. I love it. I'm going to go out and find an account and put some money in and just let it sit, because 16,000, I like that much interest. Let's check the future value equals, there's the present value times, in parentheses, 1 plus our teeny period rate, close parentheses, caret, that's our exponent, and we're going to raise it to the total number of days, which is our total number of compounding periods. And when I hit enter, check, all right, the power of compounding interest and number of compounding periods per year at 365. All right, let's go look at example number 5. All right, if you deposit $125,000 in an account for 35 years that pays an annual rate of 5% compounded quarterly, what is the future value? Compounding periods per year. Quarterly, that means 4. Years, 35. That means the power of compound interest will have a long time to build up. So even though we put $125,000 in, I'm imagining that the future value is going to be pretty big. Now, our period rate, there's the annual rate divided by 4. 1.25 per quarter. Total number of periods, I'm going to take 35 years times 4 quarters, and there it is, 140. Now we can use equals FV tab, period rate, comma, NPER, comma. We don't have any payment, comma. Present value, this is negative again. This is another investment example. We put 125,000 in at time 0. Close parentheses. Drum roll, please. There it is. 711,564 and 83 pennies. That is the power of compound interest. Actually, if we round this, come to the end, comma 2, close parentheses, the variable that influences future value most significantly is not the amount. It's not the interest rate. It's not the compounding periods. It's the years. It's actually the combination. It's that right there. The more total number of compounding periods, the more the interest on interest can build up. Now let's figure out how much total interest. There's the total future value, and there's how much we put in. That is a lot of interest. Check the future value. There's the present value. Times, in parentheses, 1 plus our period rate, close parentheses, caret, and there's our 140 for total number of compounding periods, and enter. Check. Now, we want to go look at an example on FV6. And this is an example where we just put some money in to a daily savings account at 3% for 2 years, and there's our 365. Let's go ahead and calculate this, and we'll be able to copy this down and calculate the amount for both accounts. Equals total number of years times number of compounding periods per year. That's the total number of periods. Tab, the rate, That's the period rate. So I'm going to take annual rate divided by number of compounding periods per year. Tab. The future value equals FV. The rate, there's our period rate, comma. Total number of periods, there it is, comma, comma. Minus, because we're putting money into a savings account, there's that 12,000. Close parentheses. Tab. Actually, let's F2 and round this. Comma 2, close parentheses, and tab. Our total interest, there's the future value minus the amount we put in 2 years ago. Control Enter. There's 4 different formulas. I'm going to double click and send it down. Go to the last cell and hit F2. Actually, I need to do that for both, so I'm going to click over here, F2, tab, F2, tab, F2. Looking good. Now I'm going to check it. Equals, and there's the present value, times in parentheses 1 plus our period rate, close parentheses, caret. And there's 730 compounding periods, or for us, days. Control Enter and copy it down. That is our check. Now, in this daily savings account example, we were just given years. But let's go look at our last example on FV7. And here we just know the date we put the money in the bank and the day we withdrew it. So you could see here, we only left it in for a few days. We can still calculate future value and total interest. Now, total number of periods, hey, we're going to do date math. There's the later date minus the earlier date. Tab. 21 days we left it in. Period rate, equal sign. There's our quoted annual rate, APR, divided by, and I'm going to type 365 in. Tab. The future value equals FV. There's our rate, period rate, comma, total number of periods. Wow, just 21 days, comma, comma, minus, because we put this in as an investment, 4,850, close parentheses. Let's round this while we're at it. Comma 2, close parentheses, and tab. Total interest equals, there's the future value just 21 days after we deposited it. And there's the present value. Tab. $9.78. Still, I like that. That's almost 10 bucks of interest for 21 days. I'm going to check it. There's the present value times, in parentheses, 1 plus. There's our period rate. Close parentheses, caret. 21 days. Control Enter. Oh, look at that. F2. I forgot to hit the Shift key. I should have been using the keys on the number pad. There we go. Control Enter. Looks like it's checking out. Now I'm simply going to copy all of these, including that space right there, and copy it down. F2 tab, F2. All of these are looking good. All right, so that was a lot of fun with compound interest and future value. There are a bunch of practice problems for you to do, 6 in total. Now, in this video, here on future value 7, we saw how to do the future value of a daily savings account when we were given days. Back on 6, we did future value for a daily savings account when we had years. And on a number of sheets, FV5, 4, 2, and 1, we saw how to use both future value function and the math function, either for an investment or debt to calculate future value. We also, very importantly, on FV3, saw visually a chart that shows the power of compound interest. Back on formulas, be sure to look at those PDF notes. There are some good notes for our formulas. We talked about the importance of using the wallet purse trick to determine cash flow direction. We talked about the new terms that we're going to use in the next couple videos when dealing with compound interest. And very importantly, we talked about the two sides. Remember, there's the debt side and the investment side. And when you deposit money in the bank, you actually are making an investment as long as the account pays interest. And of course, when we borrow money, we're on the debt side. Now, if you like that video, be sure to click that thumbs up, leave a comment, and subscribe, because there's always lots more videos to come from Excel is Fun, including, you're not going to believe, the next video, Math Video 44. We won't solve for future value. We'll actually solve for the present value, which will give us the ability to know how much to deposit today if we want a certain amount in the future. All right, we'll see you next video.